All right, with part two. Last chapter, we talked about ionic compounds and some of their properties, how they are usually crystalline solids, high melting points, and conduct electricity when melted or dissolved. If we look at molecular compounds, they're basically just the opposite. As you see here, they have relatively low melting or boiling points. They're usually gases or liquids at room temperatures and not solid. And usually, instead of forming a formula unit, they are going to be what's called a molecular formula because the molecular formula will show how many atoms of each type the molecule actually has. If you look at, like I said, water's H2O, two hydrogen, one oxygen. Here, oxygen has six valence electrons. It's going to share one with this hydrogen and one with this hydrogen to make its eight. Remember, hydrogen only wants to have two, so everybody's happy. What we want to be able to focus on after drawing these pictures is the number, how many atoms are bonded and how many unshared pairs of electrons there are, because that's going to give us the shape or the molecular geometry. Just remember number of bonds that they can do. They can have a single, double, or triple bond, where a single bond is one pair of electrons, a double is two, and a triple is three pairs. Just notice that's 2, 4, and 6 as far as the number of electrons, because you're still trying to get to 8. Memorize those diatomics that we see at the bottom there. You can have a multiple bond. Like I said, you have to have a double bond or the sharing of two pairs or 4 electrons in order for carbon dioxide to form, because carbon needs to have 8 around it, and if you count, it does. Look at the next one. Oxygen, still, there's the 6 that it has, sharing 2 from the carbon, and then the other oxygen has its 6, sharing the 2 from the carbon to get to 8. When you draw these dot structures or Lewis structures, you need to do a couple of different things. We need to know the number of valence electrons. That was a big point in the last chapter. Count up the total of number that it wants to have. That's following the octet rule. Everything's going to want 8 except for hydrogen, which is happy with 2. Subtract the difference between those, divide by 2, because it'll tell you how many bonds to show in your picture. After that, you fill up the rest of the valence electrons till the atom is happy. 8 around everything except for hydrogen. Once it makes a bond, hydrogen is done. So here are the two. This is the dot structure we just showed. Most of what you're going to see in your literature that I have given you is going to be called a Lewis structure. The only difference is you put a line to represent the shared pair of electrons. So each line represents 2 valence electrons. So as we move on, there's 2 different types of bonds that actually form between the sharing. One is called a sigma bond, the other is a pi bond. Sigma bonds are in the plane of the axis between the 2 nucleuses. Every bond will at least form a single bond, which is a sigma bond. After that, if you have a double or a triple bond, it's going to be a pi bond because the area that is directly between the nucleus is already taken, so it has to go above or below. Said, look at the pictures on the next one. Here is a sigma bond. It will have to exist in between the nucleus. Once that's taken, the other 2 that bond will have to go above or below in order to make the double or triple bonds. So one way, all I really had you guys do with this is count the number, where single bonds are 1 sigma, double is 1 sigma, 1 pi, and a triple will be 1 sigma, 2 pi. You still have to equal the total number of bonds that you did in figuring the Lewis structure. VSEPR stands for valence shell electron pair repulsion theory, and it is a theory to help us represent what the shape looks like. And these are 3-dimensional shapes. That's why I had a hard time drawing them, because I'm not a great drawer to show 3 dimensions. And a lot of times we draw a Lewis structure, a 2-dimensional is fine. But when we're actually trying to figure out the shapes and bond angles, we need to use this VSEPR theory. And basically says they want to be as far apart as possible. Obviously, the ones that are bonding have to be close together because they're sharing that electron. The unshared pair that's not bonding is going to repel and try to be as far away as it can. Here's the chart that we used. I also put one in your reference, in your handouts. Just focus up here on this upper left-hand corner where it says central atom. Number of atoms bonded with the lone pair. It's going to tell you the shape. It'll tell you the bond angle. It'll even tell you the hybridization that we're going to talk about in a second too. So I allowed you to use this chart on your quiz test, all that stuff.